Okay, so this video I'm going to go through exam question 9 that was set as part of your assignment for lesson 5.4.3. So this is exam question 9 that appeared in the PowerPoint. So this question here is about electron diffraction, and I'm just going to read it out to you. And if I was doing this exam myself, I'm going to be sort of mimicking what I would do as I was reading it out to myself in my head in the exam. So in 1965, Richard Feynman proposed a double slit experiment. So if it was in the exam, I might underline this rather than wasting my time writing it down. But since you don't have a time limit and you're doing this, this is kind of the key points that I would expect you to be pulling out. This is why I don't want to see any blank answers to any questions in future, because even by reading the question, you should be extracting information to investigate the wave properties of electrons. Okay, so wave properties of electrons. The fact we're dealing with electrons tells us a huge amount of information, because we know from the data sheet we can find the mass of the electrons, the charge of the electrons, so that's quite an important bit of information. The experiment was carried out using the arrangement shown. Okay, so we're familiar with this arrangement, this idea of the double slit. Now, the beam of electrons coming in from the left, two slits, and then the detector. So this is where, in theory, the interference pattern is going to be built up. A beam of electrons was directed at a barrier with two slits. So there's the barrier and the two slits. The detector recorded the positions where electrons arrived. After passing through the slits, the following pattern was obtained. Black dots represent points where electrons were detected, and a band where electrons were not detected is labelled X, and a band where electrons were detected is labelled Y. So you can obviously see this pattern yourself, but essentially you've got, how am I going to draw this? On this detector we've got light and dark bands. Falling drawing. Okay, so this is position X and this is position Y. So X is a band where no electrons are detected, so we've got to be careful when we were talking about light and dark bands before, when we were dealing with light. We've got to be careful. In this case, the dark band in the picture is similar to the light band. Okay, so that's a bit of a challenge. Well, not a challenge, but just a little complexity. Okay, so this dark band here is where lots of electrons are hitting the screen, so band Y. The path difference for electrons arriving at band X from the separate slits was 2.5 times 10 to the minus 11. So just to kind of get your head around this, if I draw these on this screen up here, hopefully you can still see this. So what we've got is a central maximum, which is this band here. Then we've got our first order band, Y. Sorry, that's a Y. And then in between the central maximum and the first order band, we've got X. I'll just put that in front so it doesn't sort of overlap. So X here, Y here. Now, what we're being told is that at X, the path difference is 2.5 times 10 to the minus 11. So the electrons that arrive on that detector X, can I draw here? The path difference, so if this one has travelled a greater distance than this wave, the path difference is equal to 2.5 times 10 to the minus 11. And at Y, so this point here, sorry about this drawing, at Y, the path difference is equal to 5.0 times 10 to the minus 11 meters. So this is all just me extracting information from the question. I haven't done anything here, I'm just getting my head around it, okay? So you can see how much work it takes before you even start the question. Explain why this pattern is observed when the electron energy is equal to 9.6 times 10 to the negative 17 joules. And it says the electrons are travelling at non-relativistic speeds. Essentially, don't worry too much about that now. All it means is that we can use the mass of the electrons from the data sheet. So what we're going to do here is we're going to take this energy and we're going to work out from this energy the wavelength that these electrons must have. Okay, so because these are being accelerated, or these electrons are moving, this energy is in the kinetic energy store. So what I can say is that this energy, which is in the kinetic energy store, is equal to half mv squared. Now, I know the energy, I know the mass of an electron, I'm going to look it up in a second, and I'm going to use this to work out the velocity of the electrons. So if I rearrange for V, like so, and then I'm going to substitute in 2 times 9.6 times 10 to the negative 17 divided by the mass of an electron. Okay, so because we were dealing with electrons, maybe I should have written here the mass of an electron, 9.11 times 10 to the negative 31 kilograms. Okay, I also could know the charge of an electron, but don't necessarily need that. So 9.11 times 10 to the negative 31. And if I put that on my calculator, I get a velocity of 1.45 times 10 to the 7 meters per second. Now, what's that helped me to do? Well, the reason I've done that is because I know that if I know the velocity and I know the mass of something, then I can work out its wavelength. Because if we remember de Broglie, I always want to say de Broglie because that's how I always said it, but de Broglie's equation, we've got that the wavelength is equal to Planck's constant divided by the momentum. And we remember that momentum is the mass times the velocity. So if we have the mass of something, we have the velocity of something, we can work out the wavelength. So Planck's constant, 6.63 times 10 to the negative 34. The mass of the electron is 9.11 times 10 to the negative 31. And the velocity that we've just worked out over here, 1.45 times 10 to the 7. Again, put that in your calculator, and we're going to find the wavelength is equal to 5.0 times 10 to the negative 11 meters. Right, where does that get us to? Let's just recap what we've done. We've been able to take the energy that we're given, and we've been able to work out the velocity that the electrons must have been travelling at for that energy, and from that we've been able to work out the wavelength. So now we think back to our, this is where we go back to what we learned about Young's double slit experiment in chapter 5.2. And let's take at position X. So at X, here, halfway between these maximums. So at X, we know from the question that the path difference is equal to 2.5 times 10 to the negative 11. Now, if you look at how that compares to that, you will notice that that is half of the wavelength. Okay, 2.5 times 10 to the negative 11 is half of 5.0 times 10 to the minus 11. So when we have a path difference, okay, so that's the difference in the distance travelled to X between this wave and this wave. When we have a path difference of half a wavelength, we know that that tells us that the electron waves are out of phase. Okay, we can write this as are in antiphase, or we can say 180 degrees out of phase. It's the same thing. And if we have waves that are out of phase, 180 degrees out of phase, arriving at the detector, what will happen is that we will get destructive interference occurring. Okay, and that's why at X we've got a region where there are no electrons incident on the detector. So this isn't necessary to get the marks, but let's just go through this process for Y as well. So Y, well, we're told in the question at Y the path difference is equal to 5.0 times 10 to the negative 11 meters. Let's compare that to what we calculated as the wavelength of the electrons, and you'll notice they're exactly the same. So the path difference is equal to 1 whole wavelength. So we know if the path difference is equal to 1 wavelength, then that means the electron waves are in phase with one another. And when we have waves arriving in phase, that means we get constructive interference. And that's why we've got at Y a band where lots of electrons are incident on the detector at that point. So in terms of marking, this is a 6-mark question. So let me just get the mark scheme up. The first mark is for your use of the kinetic energy formula. So that would be this step here for mark 1. The second is your use of the de Broglie equation. And the third mark is for doing this calculation and getting the wavelength calculated correctly. The fourth mark is for working out that at X the path difference is half of this calculated wavelength. The fifth mark is for realizing that a path difference of half a wavelength means that they are 180 degrees out of phase. And then lastly, mark 6 is for identifying that if two waves are arriving out of phase, then you get destructive interference. Okay, these points below, you don't need to do both, but I think it's good for completeness. So that's mark 4 again, mark 5 again, and mark 6 again. Okay, I hope that helped. I'll upload an image of this as well, so that you have it to refer to, and I will supply you with the mark scheme in the examiner's report as well.